Okay, so it's my pleasure to have our next speaker that is giving a mini course, Michel Brion, and is going to give a mini course on the introduction to spherical varieties. Michel.
Thank you very much. Thanks for the invitation. I'm very happy to be here. And probably by the end of the week, I will have a better idea of the topic. I have to learn many things. And okay, so this is some kind of basic introduction to spherical varieties. And it will be a very limited scope. But I realized by discussing with people that many topics other advanced will not be covered in this course. So I'm of course open to discussions, seeing new things. So let me start with a kind of model case, which is projective homogeneous varieties. So I will work with the complex numbers in this talk. Many results extend to algebraically closed fields with some efforts, and to arbitrary fields it's just another matter. So let me consider variety X, as the title suggests, as the quotient of E by some E. So D is a connected linear algebraic group. And P is a so-called parabolic subgroup, which just means that G mod P is projective. And we can replace G by some quotient and assume P semi-simple. Then one knows many important results about these varieties. One of them is the Brion decomposition, which I will just recall in a very non-effective way. So I will choose a Borel subgroup B. As you know, it's a maximal connected solvable group, and it's known that it's a semi-direct product of unipotent parts by maximal closures. Okay. Now, the Brion decomposition tells you, in particular, that X has only finitely many E orbits. Actually, it gives you much more information on the D orbits, and these are also orbits of this subgroup U. The point is that each B orbit is a B orbit of a special point, which is fixed by this maximal torus T by construction. So you get only U orbits. And in particular, these orbits are affine spaces. E to some power. So what you get in this way is a cellular decomposition. Of X into some so-called Brion cells. This has many strong consequences. I will mention just a few of them. First of all, if you're looking at the Chow ring of X, this will be notation for Chow ring. This has basis the orbit closure. The free abelian group generated by the classes of orbit closures, which are the Schubert cycles. And it's isomorphic to the common view ring, so degrees are double to the cycle map. So we have this description, and if we are interested in the cycles of codimension 1, what we get is of course a Victor group. What we obtain is a natural basis. Maybe I write it in this way. These are the classes of Hilbert devices. Okay. These are the closures of the set of codimension 1. And also they generate the positive, well, I think the correct word is NEF. NEF means having non-negative intersection with any curve. And so the ample cone of X is the interior of the cone generated by these classes. So that's a very nice picture. So we will see that this picture extends to many interesting varieties, including wonderful varieties with some adaptations. So here is a kind of a model case. I should also make the structure of the open cell precise. So open this is just the open B orbit here. Well, to describe it, you choose a parabolic Borel, which is kind of opposite to P, and the precise meaning is this. You take a Borel of an opposite parabolic. This means that the intersection of both is a Levi subgroup of both. That's the definition of opposites. And now the open Breuer cell is just isomorphic to the unipotent radical of this two. That will be my notation for unipotent radical. Okay, and now the isomorphism is what you might imagine. You have V, which is a Borel of this group Q, which is just unipotent radical of Q, so maybe like for that please. This L. And this fixes the point you're considering, so you're left with this part. So this is also some very nice information. We have an explicit description of the open orbit, the open part, and we'll see that this also extends to more or less all spherical varieties with some additional information. So that's again kind of model case. And now one possible way to generalize this nice class of varieties would be the almost homogeneous varieties. So this will be my next things I would like to discuss next. So the definition is just straightforward extension of the homogeneous. You still consider a connected linear algebraic group. Which acts on some divide X. And you assume that there is now an open orbit. So my notation for orbit will be G dot some point. And as you know, this is just a homogeneous space, a quotient of G by the stabilizer, G sub X. And well, I will fix this stabilizer and call it H. Okay. So that's what we think of. And of course, there are some nice classes of almost homogeneous varieties. The ones you certainly have seen or heard of are toric varieties. So here you take for G a torus. In this setting, I just write something like this, called T. And so you, well, and X is usually assumed to be normal. This is a mild restriction, which allows combinatorial classification, which I will maybe not recall here. Fans. Well, maybe I'll not really need this, so I'll just skip it. But important consequences: you have only finitely many orbits. Isomorphic to C star to some power m. Okay. So you have a decomposition, a finite decomposition by pieces with simple structure. So that's also very remarkable. And if X is smooth projective, what you get is even a cellular decomposition. By T statement, maybe I could add this. So it means you can put these orbits together in some way to get some affine sense, and it will be paved by this sense. This is well, the general name is. Let me try to write it correctly. And then you correct me. There are some Polish mathematicians especially correct me on that one. But I think I get it. And this decomposition holds, sorry, for all smooth projective varieties with an action of a torus with finitely many fixed points. And here you just get this. And it's stable by the whole torus. So, but it's a very nice ingredient. Another ingredient which is quite remarkable is for a toric variety, you can get the torus action out of the abstract structure of variety. So for X, say projective, the torus action on X is unique up to conjugacy by automorphism. Actually, this is also true for X affine, I guess, but the proof is harder. Here I can give you a proof because it's one line. You have T sits in this group as a maximal torus. Which is very easy to check. And then maybe this group is too big, but you take the connected component as in Gauss talk. And now you have an algebraic group, the maximal torus, they are all conjugate. That's it. So you get an extremely beautiful picture for toric varieties. Well, if you go away from this, we can get some much more complicated behavior. I will just mention it because it is something to keep in mind. So let me discuss very briefly equivariant compactifications. Of vector groups. So that for the background. This is a very long name, but that tells you that in the situation of almost homogeneous varieties, you take G to be the additive group Cn, and H is 0. Right? So you just compactify Cn equivalently for the action of Cn on itself by translations. And then if you think about it, you imagine many examples, because you have the projective space by action or by translations. You have the dual projective space, which is both are not the same with respect to translations, if you think about them. You have quadrics. If n is a product of two numbers, maybe p and q, what you can imagine is the Grassmannian. Maybe this is not the standard notation. Look at the Grassmannians of subspaces of dimension p in a vector space of dimension p plus q. And this contains, as you know, it's an open subset. We put this kind of matrices. Use this as this set of matrices and take the open orbit of this. And then you get an equivariant compactification of this group, which is just yeah. So you get all these examples, and out of them you can get more because you see G fixes pointwise the hyperplane at infinity of Pn by acting by translations. So what you can do also is blow up everything you like in this hyperplane. So this is a new equivariant compactification, which is smooth, if Y is smooth. And in this way, you also see that you will get sooner or later some varieties which have no cellular decomposition. For example, you take Y to be a smooth curve of genus bigger than 1, and n bigger than 3, so that you can put it in P2. You put someone like this in P2 and blow it up. Then what you get is that this has no cellular decomposition. Otherwise, you would have a cell which maps dominantly to Y, and this is not possible because Y is not rational. So you see, you can get more and more complicated objects, and actually, even the actions of Cn on projective space Pn with an open orbit have been described by Hasselt and Michel. A very nice paper from this year, I guess. In terms of commutative algebra, and this shows that if n is bigger than 6, there are moduli. There are infinite infinitely many non-conjugate families. So it's really very different from the toric variety part. So that was just for small things to keep in mind. And now I would like to discuss one class of varieties which have has very nice finiteness properties. It's spherical varieties class. So now G will be reductive. By convention, it's connected, right? And I will choose a Borel subgroup as above with this decomposition, and I will say that a normal variety X is the action is spherical. If it has an open B off. So this is a kind of tricky condition because you don't consider the full action of G, but the action of much smaller subgroup. But you will see by practice that it guarantees many nice consequences, and it rules out all these problems we saw here, basically. So I should give you some examples. So here is a long list. Of course, you get projective homogeneous varieties. Just by the Brion decomposition, you get, of course, toric varieties because then G is B. Everything collapses. So that's kind of maybe case. And well, maybe morally, a general spherical variety should be some kind of mixture of both, but it's not really like that. Okay, so well, for some aspects it's close to the truth, and for some other aspects it's a bit misleading. So I don't know what to think, but I will give you some further examples to see what can happen. So, a rather nice example is DLN, with the action of DLN times itself. And the action is by left and right multiplication. Well, here for notational purposes, it's a bit awkward because everything is doubled. So you have to take a Borel subgroup here and then maybe another one here. But then there is an open orbit by the Brion decomposition. You have B times some general element times B is open GLN. So that's one example. Another example from maybe geometric origin is GLN modulo orthogonal group. This is my notation for orthogonal group. And you may think of this as a space of quadratic forms, non-degenerate. Quadratic forms. Many variables. because GLN acts on this space of forms by change of variables. And, as you see, there's a big orbit on the stabilizer, sum of squares. The stabilizer of the sum of squares is ON. And now the similar argument shows you that inside it you have an open orbit of a standard Borel of GLN. Here B is so many times probably this kind of matrices. And you see this B as a stabilizer of the standard flag. Corresponding, it's a flag of this subspaces. This just tells you the matrix is upward triangular. And then the claim is this open orbit is the space of quadratic forms, such that the restrictions to all these elements of the flag is non-degenerate. So that's a claim that if you look at this subspace of quadratic forms inside the pool one, you get a unique B orbit. And if you think about it, it's just how to write a quadratic form as a sum of squares by the usual algorithm. Okay, so it works well if this happens. Otherwise, you have to change basis. Okay, so it's nothing. There is nothing deep, but it shows this observation, and this group B intersected with ON. You have orthogonal matrices which are upper triangular, but you get this diagonals of plus or minus one matrices. Okay, so it's a group of order 2 to the power n minus 1 because n in GLN. So it's a finite group. So you have this quite nice decomposition. And to finish this, two additional examples which I should mention. There are symmetric spaces. These are just G mod H, where H is fixed points of evolution. Okay. We will see maybe in more detail why they are spherical according to this definition. Of course, these examples above fall in this category because for this one you take the involution of GLN times GLN, which exchanges both factors, and for this one you take inverse transpose. Okay, involution of GLN, which fixed points here. So this another class which will show up in this course and shows up naturally. And a final one is homogeneous spaces. These are space like again G mod H, but now we impose that H contains the group U, which is a unipotent part of the Borel. Right? Or conjugate, it doesn't matter. but the important observation is this space contains finitely many d orbits. There is a Brion decomposition where u or b don't play a very different role. So this is really something easy. But now there is a very strong consequence that we see that every spherical homogeneous space contains only finitely many d orbits. Okay, so that's probably the first non-trivial result of this theory, which is very old. Well, there are several proofs. Maybe the nicest proof is you start with a spherical homogeneous space, G mod H, and you produce some kind of degeneration to a horospherical one. I will come back to this in the third lecture, with details, but once you get the idea, you just use some semi-continuity arguments with a little bit of care. Since you have finitely many orbits in the special fibers, you should have finitely many in the general fiber. Okay, so that's the idea. Here I'm really cheating, but not too much. Well, I'll come back to this. So that's the first kind of important finiteness statement. So now I would like to show that this extends to spherical varieties, not only spherical homogeneous spaces. And then there is a small thing to do, just to show that every spherical variety has only finitely many d orbits. Then you can put those things together, and this is well something I will also check. Sketch a proof in two steps. First of all, I will discuss the fine spherical varieties. You will see these are very closely related with some kind of basic representation theory. So I think it's interesting to see this. So let's consider a fine variety. There is an action of G, which is again a reductive group. And then G acts on the ring of regular functions on this variety. This will be my notation for this. This was K bracket G fx in the previous talk. Anyway. And this makes O of X so-called rational G module. Since G is reductive and we are in characteristic 0, we can decompose it into irreducible or simple representations. So this will give you something like this. This will be a sum over all dominant weights of multiplicities times irreducible representations. So the notation is as follows. lambda plus is a set of dominant weights. This will be a subset of lambda, which is a set of weights. This is a character group of B. And for any such dominant weight, you have a irreducible representation with highest weight lambda. And these are just multiplicities, are integers, well, non-negative integers, possibly infinite. Well, here I'm not too, I'm a bit sloppy with definition, but now there are two observations. If X is almost homogeneous, this implies that all the multiplicities are finite. Well, this is a nice fact, but it's not really deep because it's already like that with the group. If you maybe you remember the decomposition of G as a representation of G times itself. This is something like this. It's an algebraic version, but better vibe theorem, I think. Okay, and if we keep only the left G action, when you get this with multiplicity, the dimension of this. So that's not a big fact. And there is no converse here. You can pick up permutations is finite multiplicity, but not almost homogeneous. But for spherical varieties, there is a nice converse. X is spherical. If and only if you have two conditions. First is m lambda is 0 or 1. Well, if you look closely, this is equivalent to X having open B orbit. It's not a difficult fact. But then in the definition of spherical varieties, you also have a normality condition. And this gives you the second condition. The set of lambda such that m lambda is 1 is a set of irreducible representations which do appear. This should be the intersection of some lattice with some cone. So let me explain. So this is a sub-lattice of a great lattice, and this should be some convex cone. If you're familiar with toric varieties, you have seen these objects. Okay, when you classify a fine toric varieties, you get exactly this. And well, of course, there are choices for these pairs, but you have a unique minimal choice. Take this lambda object to be generated by this set, and take the cone generated by this. So here you may assume that the cone is a rational polynomial. So that's something which really directly analog to toric varieties. Okay. Now I think I can maybe state a corollary. Say that X affine spherical. Then it has only finitely many G orbits. Okay. Just like in the toric case. Well, let me sketch the proof. Probably you already imagined the proof. So what we actually prove that is that X has only finitely many closed G-stable subvarieties. Shall we call Y? If we prove that, then we have only finitely many orbit closures. That's it. And now this is some statement which is much closer to algebra, because as you know, Y corresponds to its ideal in O of X, which is prime this table ideal. Okay. Basic that, and you see this O of X is a sum of V lambda or lambda in this combinatorially defined set, and why this ideal being G stable is just a partial sum. Okay, so but then you have to manage so that this partial sum defines some prime G stable ideal. And now the trick, but the statement is you only are allowed to consider a face of this cone. So let me write correctly. You sum over lambda x and you sum outside the face. And the reason is as follows. You have this C of X is a convex cone like this. And you have an ideal which corresponds to a partial sum. When you take the quotient, well, you take what's left. And what's left should be some ring with no zero divisor, because you have a prime ideal. And by multiplicativity properties of this decomposition, you cannot, you only can have a face. Otherwise, you get two things which multiply by zero. So the main point or the main ingredient is to use this ring of U invariant functions inside this O of X. And since you have this sum, what you get is, of course, the same sum, but with U invariance. But now, if by representation theory, if you take U invariance there, you get a unique line. This is a line of highest to 8 vectors. So let me write it formally like this one. And these V lambdas multiply in the non-zero way, because you're in a coordinate ring of an affine variety. So you have a scalar times V lambda plus mu by uniqueness by square vector. And that's the reason why this argument works. Okay, so that's was very sketchy. But you see, for toric varieties, you can get all the faces by the same argument, because you see this many things collapse. And for toric varieties, this is just one line. So this story describes you everything, and you get all the faces. For spherical varieties, you don't get usually all faces. So there are restrictions which are a bit hidden. Maybe I won't discuss them right now. What I want to explain finally is how to get from a fine spherical varieties to general ones. Okay, and this will be so-called local structure theorem.
It's me.
Yes.
If we consider that convex cone with the lattice, you can hook up a toric variety.
Mm-hmm.
Is this toric variety related geometrically to the affine variety we started with?
That's a great question, and it's related. We have this horospherical degeneration.
The one that you mentioned.
Yes. Well, so let me finally give you more details on this horospherical degeneration, but just by hand waving. Okay.
But you said lecture 3.
Yes,
So
but
we can wait.
But well, here it's very simple to imagine, right? Okay, because you see this decomposition. In this decomposition, the multiplication is a bit complicated, because if you multiply v lambda and v mu, these vectors, these modules, you get v lambda plus mu by this formula, maybe plus other stuff. Okay. Now you hook up flat degeneration by killing all this other stuff. So at the limit, you get that things multiply in a naive way. And that's exactly this horospherical degeneration. And now the toric variety gives you everything at this limit. Originally, it's a bit okay. So is it okay? Or maybe otherwise you can always ask questions for likes, whatever. So let me finally explain this local structure theorem, which tells you that locally, in some sense, spherical varieties reduce to affine spherical varieties. But for this, you have to change the group and do something. So the setup is the following. Let's take a projective spherical variety. And for G, and let's take a closed G orbit. So this already exists, and closed orbits exist in the realm of algebraic group actions. So now you know that Y is isomorphic to G times some parabolic subgroup, which is a stabilizer of some point. Okay, and as in the Brion decomposition, I will consider the opposite parabolic subgroup to this gy, and for notational purposes, I've just denoted by P. Again, this means that intersection of both is a Levy subgroup L of both. So that's just notations, and now the statement of the theorem is the following. there exists a fine n-stable subvariety S in X, that goes through this base point Y, and it describes the structure of X along Y in the following way. You have the unit radical of P times S, which is mapped to X. That's just a group action, basically. And this map should be an open map. Okay, so that's something maybe we should deserve some. So maybe it's not a completely obvious statement to understand. So let me try a attempt of a picture. You have your big variety X. You have your orbit Y with a point here, which is a homogeneous variety. And inside Y, you have the open Brion cell, which is maybe a this will be by what we saw, the orbit of Y by the unit radical. This is the open Brion cell here. And the statement means that you have a kind of transversal subvariety S, but that's an open subset which hits the Y exactly along this open Brion cell, and which is a product. So the factor is like this. Well, the picture is not so great, but I want to stress it's not a kind of slice theorem like you see in differential geometry, where you think that an orbit along an orbit, a variety looks like the normal number. Here you have to take an open subset, and then you have a trivial decomposition. So it's a kind of different gadgetry. But anyway, you see that many properties of X reduce to properties of S. Here you have a G action, and here you just have an L action. And now the remark is that with this notation, X is a spherical. S is L spherical. Because having an open V orbit can be tested on something I should have said, that this I forgot an important information. Here you have an action of P on this he acts on this by its semi-direct product decomposition. Unit radical acts by translation, L acts by conjugation.
Is Y any closed orbit? The orbit? Or
yes. So this is really in the neighborhood of the orbit, not in a global sense. And what I want to stress is that the image of this map is an open p-stable subset.
So I'm confused. Which bit does Y live in of the two factors?
Sorry?
It's in S, or are you a P?
no, it's
This small y.
No, the big Y.
The big Y.
Which direction does it lie in? You've got two factors there.
Well,
Mr. Dwight, sorry.
maybe this answers your question.
Thank you.
Okay.
Yeah.
And I should have this. I've said it again earlier. Thank you. So if you restrict to y, you get the open set. That's what I wanted to explain with this picture, but I realized it's not such a great picture. Okay, sorry. Anyway, I think now it's clearer. To make things explicit, I should say this open, this p stable element.
Is that the equivariant?
Yes, here you have the induced action, and here you have an action of P. Let me say it. P is a semi-direct product. Right, yeah. Yeah. P is okay. Now this one acts on this product just by translation on the first factor. And this L acts by conjugation here and action here. So let me write it L. So L. Here. Ah, okay. It's better not to write. Otherwise, I get confused. So this one again acts by left multiplication, and this L acts on both sides. So I hope now it's every ingredient is in place, and I see it's not such a trivial result, but still the conclusion is clear from this that every projective spherical variety contains undefinitely many because we had this for affine ones, and we just use local structure theorem. You see that okay, you get only finitely many p orbits. P orbits are still. No. So here, by the theorem that I stated, we get the same with b orbits. Now, there are some further corollaries that I should mention finally. Pretty good projective. And spherical variety. The B stable cellular decompensation. Okay, it is something very useful for topology with varieties. You see this out of this. Well, you have to realize that your variety has only finitely many fixed points of a maximal torus T, right? And you compute these fixed points by B orbits. And it's a simple exercise to show that in each B orbit, you have at most one T fixed point. Okay. So now you get first of all, the fixed point of T is finite. That's what I just mentioned. You decompose into the orbit. Look, and then to apply this Jaliniki-Birula decomposition, you have to choose a general one parameter subgroup. This means outside of some, so this one parameter subgroup from a lattice, and you choose it outside a finite union of sublattices. Okay, and every one of them will work, and you choose its regular dominant. And this means that the set of G in G, so that this is exactly the group blue we are discussing, because well, that's a simple exercise with roots. And now by this convention, you see that Jaliniki-Birula decomposition is U-stable, because it's constructed in the following way. Take a fixed point, X, and look at the points which are attracted by this line. If you apply lambda to this point and go to 0, you have a limit. You want and this limit is exactly your point X. And by a simple computation, this cell is stable by this subgroup here. That writes some conjugation. And so you see the cells are U-stable. They are also T-stable by another easy computation. So you get everything is B-stable. And that's why this works. Okay, so sorry, the other signs I can start. Thank you.
So in this corollary that it's spherical variety means only finitely managed orbits, how important is the projectivity essentially?
Sorry, not at all. Because given an arbitrary spherical variety, first of all, you can always cover it by open quasi-projective varieties. That's a consequence of a general theorem of Sumihiro. And given once it's quasi-projective, you can find a projective equivariant completion by another standard trick. So if you put both together, you get a complete proof. But you're perfectly right. I should put this when there is a parameter this, but I will check. Thank you.
Other question?
For toric variety, the canonical class as a representative given by the toric divisor. Here are there some nice representative of actually the anti-canonical class.
The anti-canonical class is a sum of G-stable divisors with multiplicity 1 plus a sum of B-stable divisor with multiplicity which are positive but not too well understood.
And do we know something about the positivity? Or?
Well, it's a general fact. that if you have an almost homogeneous variety, minus k is always big. Okay, it's not a trivial fact, but it's true. And so for spherical varieties, minus k is always big. Then for some classes of spherical varieties, they tend to be log Fano. If you look at their device, at their boundary as a G variety, so the log minus k, this one is ample. Probably I can show it tomorrow. I don't swear it, okay? Or give an idea of the proof. So they are uniformly log Fano, and then wonderful symmetric varieties tend to be Fano. It's not completely true. Okay, sorry. It's a kind of complicated business. They are always weak Fano in the sense that minus k is globally generated and big. It's a general fact. And most of them are Fano. And there is a criterion, combinatorial criterion for them. For spherical arbitrary varieties, it's not so well understood. I think the only uniform statement I know is log Fano. This works well.
In the set of isomorphism classes of spherical varieties countable?
Yes, this is morally true because of practice. You see, you have some local invariance by these codes and so on. And there is a proof in a paper by Alex Eliaf and myself from 2004, which is a kind of non-trivial. You have to use information theory like Hilbert schemes and arguments to do this.